Okay, so little reminders. Homework B1 is due tonight. There is a bonus, which if you haven't figured out on your own, I will give you some tips to the bonus in today's lecture. The Canvas assignment will automatically, the Canvas will automatically assign a 0 if there's no submission after the assignment is due. That's just how Canvas is set up for convenience. But if you do happen to turn it in after the after the due date, then that submission will end up getting flagged for grading, and then your grade will replace that 0. So remember that for homework assignments, there is a late assignment that. So I say no penalty if submitted during the availability window, but it's with the there is a late penalty, but I'm trying to say that when the 0 shows up, you're not going to get the 0. So as long as you submit it during the availability window, then you'll get graded as it says in the syllabus. So if you turn it in before 10 a.m. tomorrow morning, you'll get graded for full credit. If you turn it in after that, 80% the next day, 60% the next day, 40% the next day, 20%, and then it disappears. And at the instant it disappears, then the solution set will appear. So that's how that works. There's a new ICA, again, healthy drop policy on ICAs. So you don't have to do them, but they're just meant to help you sort of keep up with what's going on in the book in parallel with what's going on in lecture. So for those of you where, I'm not quite doing it for you, hopefully the book is a good complement to that. We're going over a lot of the same topics. Then lab 3 this week. This is our first exposure to automating simulation runs. So lab 2, as we'll talk about at the end here, was about hand simulation, just like we've been doing in the homework. Lab 3, we're actually going to start doing Monte Carlo runs, where you'll actually use Excel to generate some stochastic data that we'll end up making inferences about. So it's not a dynamic simulation, but it is an example of a type of a simulation method. And so that will be lab 3. So then lab 4 will be our introduction to NetLogo. And then lab 5 will actually be our first introduction to Arena. So that'll be that if you want to have Arena easily available to you, it's good to make sure it's available before lab 5, which will be in roughly 2 weeks. All right, so that's that. Again, I'll mention again, there is this Rockwell Arena competition that is available. The entry forms are due at the end of September. If you end up taking this class and decide that you'd like to participate after you've learned Arena, then you can actually participate in the winter session, so our spring session. So there's you don't have to be in class to participate in this competition, but if you want to participate in this competition as your final project, then that is something that is definitely possible to do. There's also FlexSim, which is a competitor Arena, and Simio. They also have their competitions, and we can talk about using those for your final project as well, as we talked about before. So that's, I think, up to date on announcements and policy. Any questions? I hope the lab setup's been working well. It's supposed to be flexible, provide you support when you need it, but not force you to attend a 2.5-hour lab when you don't. So understand that there's been some people have been working with the TA, but others have been just going on their own, and that's totally fine. But of course, if you need anything, we're in the lab things, feel to reach out to the TA and reach out to me so we can help you with those assignments, which are, again, complementary to the lecture material. They provide a little bit more applied exercises rather than just what we see in the homework. Okay, so I'm going to skip this one for now. Last time we left off, and I'm not going to step through this whole process again, but just to remind us, the idea was that you filled out this table. This is very much like the homework assignment. So I gave you an end time for the simulation. I gave you this table. Although these numbers are organized by customer, you shouldn't sort of think of them as being coupled together. Whenever you need a new inter-arrival time, you just take the next one off the list. Whenever you need a new service time, you take the next one off the list. It is the case that the service times kind of go with the customers, but it's not like you go back and forth between these, because it might be that you hit multiple inter-arrivals before the next customer is finally ready for service. So it's kind of a way to read that. But if I give you this and I give you the end time, then it's possible for you to fill out this table where you're doing the process that Arena does when you draw the simulation and hit go. And so that ends up, generating a timeline that looks like this, where in this case, the sim is ending at time 15, but there's still events after that in the event calendar. And then once we run a sim like this and generate this event calendar, then we can start noticing interesting things about the output that we can then potentially suggest ways to improve our system. So when I look at this timeline, I see that these arrival events, well, those are spaced out. Those are activities. Those are things we know ahead of time. So the distance between every arrival event comes directly from this table. And because arrivals just can happen kind of immediately, then there's no gaps in between the arrivals. So we actually know, just by looking at this table, it's easy to check. If we sum all these things up, we can figure out what the arrival time of, we know that, if customer 1 arrives at time 0, customer 2 will be at 4, customer 3 will be at 6, customer 4 will be at 7, and customer 5 will be at 16. And that's what we see here. So, effectively, these times in the middle here in these event records are just summing up the inter-arrival durations. And we'll see that when we do the spreadsheet example here in a bit. So these are activities. We know them ahead of time. We didn't have to run the sim to get these activities. They were given to us. And so activities, durations that can be estimated without running the sim, unconditional weights. And then we also have these activities. Now these, we don't know when they start. We have to run the sim to figure out when they start. But once they start, we know how long they're going to take, and that allows us to schedule new events in the future. So we know that when customer 1 started their service, that comes from the table. It takes them 1 minute to start their service, so they're out in 1 minute. We don't know when customer 2 will start their service. We have to figure out when they arrive and if the system is available at that time. But if it's available when they arrive, their service can start, and their service will take 8 minutes. And so that's why they arrive here. The service is available, it takes 8 minutes, and so on and so forth. So all of these red durations, those are also activities. We know their values ahead of time without running the sim. But we don't necessarily know when they'll start. And that's the trick. That's the thing that we need the sim for, is to figure out when those activities will line up. And when they don't line up, when multiple processes that generate activities don't line up, that's where we get the true outputs of the simulation, which we call delays. And so this right here, you could think of it as a little bit of waste in our system. That means that we had a server that was available that had to sit idle for this amount of time during this delay. And there may not be anything we can do about that, or if we have a lot of servers, and if we find out that we really only need one on duty at a time, then that might mean that we reduce the capacity of that service process because we have too many of these delays. That's the sort of thing. So those delays they're looking at. So here's one that's a little bit more meaningful. Here we have customer 2 is in the process when customer 3 arrives and isn't able to start the process. So that generates a delay. That's why customer 3's arrival is separated by the time that they actually, so customer 3, they're this 1 service duration, that's customer 3 right there. That right there, that was delayed by waiting for the service from this previous customer to end. So that's what I mean by things aren't quite lining up correctly, or we don't have all of the right number of servers, and because of that, we generate these delays. Now, delays are inevitable. If we were to get rid of all delays, then we might be we kind of run into diminishing marginal returns where the cost of supporting a system with no delays won't be worth the benefit. Sometimes you just tolerate a little bit of delay. But our question as industrial engineers, as operations researchers, is whether there's too much delay and whether we're okay with this system of delays that comes out of our simulation. And if we're not, then we might go back and alter our system. So we might add more service processes. We might change the order of the way people come into the service. There's all sorts of things that we could change. And the way we will evaluate if we were successful is we'll look at the delays in our changed system, our hypothetical system, to see if we've made improvement. So delays are the outputs of our system. These are the conditional waits. These are things where the wait time is conditioned on the state of the system, and we cannot know them until we run the simulation. And that's the difference between delays and activities, and we can start to see that in these simulation executions. Okay, so are there questions about that? I'm going to summarize this in text, but while I've got this graphic up here, does that make sense? This distinction between activity and delay in terms of the simulation timeline. Okay, so I mean, written out, an activity is also called an unconditional wait. It has a predictable duration. Duration does not depend on the state of the system. We have some other terminology that sometimes is used here. So the completion of activity is what we call a primary event. So that's the thing you schedule. So there's some, when an activity happens, you then have to say, well, if someone's starting service, the way we simulate that service happening is we schedule the end of that service. And so those things that you're scheduling ahead of time are these primary events. So they're not triggered by something changing in the system. It's you saying that I am going to make the system change at a scheduled time in the future. That's due to me ahead of time. It's not due to something going on in the sim. I am scheduling it. So a primary event are the events that occur in your system because they are scheduled by you ahead of time. Now, a delay is a conditional wait. It's a wait condition on the system state. Its duration depends upon appropriate conditions in the system. It's caused by the interaction of these different processes. And so, and the related thing, the reason I bring up primary event is that there are other events in your system that are potentially generated by when the system state changes and triggers logic that is not triggered by just an activity, needing an activity to like when you're adding a duration, you say, I know that something needs to happen then, so I've scheduled that I know something's going to happen at that point. But then there could be logic that occurs when, for example, the number of people in the queue goes down to 7. Well, so that's something where the change in the state of the system generates that event. So that would be the kind of the difference between a primary event and I guess a conditional event. And so, so that's, I'm just saying why I brought up primary event. Delays don't generate events. Delays are generated by changing system state. So if I were to sort of summarize that, events terminate delays. And so when an event shows up on the calendar, at that point, a delay that's been happening, that's, let's say someone's been waiting for service. Well, if someone's service ends, well, that is an event that occurred on the calendar. Now that opens up the server for that other customer that's been waiting to get in. So events squash delays. So that's kind of the activities generate events, events squash delays is kind of the relationship there. And so we manage delays, as you're starting to see in the hand sim, by things like placing entities onto internal lists, because we don't have anything to do with them while they're being delayed. We have to wait for their logic to be triggered. So temporarily, we put them somewhere. And physically, in a real system, we put them in a waiting line. But in a virtual system, we might have a queue that we just call a checkout line, like you've seen in your hand simulation. So that's delays. And activities. Delays emerge from concurrent processes with limited shared resources. So limited resources means that not everybody is going to line up perfectly in their need for that, or everybody might need a resource all at the same time. And it would be great if we could space everybody out so that, so example, when there's in traffic engineering, you try to engineer these so-called green waves when you do traffic signal timing. And so If you know, roughly speaking, the speed of traffic on a road, then you hopefully can get a flow going where if someone hits a green, if they travel, in speeds in the expected bounds, then as they approach a red light, it'll turn green. And then as they approach the next red light, it'll turn green and green and so on. And so you get this someone that even though you've got this device that's used to maintain exclusive access to the intersection, if you've managed to space the cars out right, then they can kind of interleave themselves so that nobody actually has to stop. So, if you can manage in this sort of miracle world, initially somebody comes into your city and they have to stop at the stoplights, but then once they get that green, then they're sort of, synchronized with the rest of the city. And then that synchrony allows them kind of like a marching band to then move through the city, crossing over each other without ever actually having to stop and wait for each other. That would be the ideal traffic situation. And that would be by sort of aligning all of these activities. But that's very difficult to do. But if you have them misaligned, it's very easy to see the output of that. Then you get a lot of waiting. So a lot of, sitting at red lights, waiting for a resource to become free. So that's what we mean by delays and so on. So any questions about that? Is the notion of delays and activities becoming more salient? Okay, great. All right, this is what we did last time, and so I'm just gonna click through this very, very fast just to animate it, just to remind ourselves what we did last time, where we just talked about how there's this generic logic, which you've done in your homework now, and in that generic logic, you get arrival events, you go through a certain set of things that happen on arrival, you get departure events, you go through a certain set of things that happen on departure. Again, this is identical to what we did last time, and I'm just putting it in here as a reminder, and so it's in the slides and archived. You get end events, which just cause your simulation to end. And if you follow that recipe that I just flashed through there, then you can start with a table like this one and an end time right there, and you can gradually populate that table. And as you populate that table, you populate this event calendar down here, and eventually you generate the whole simulation output. And that's what you did in your homework for homework B1. That's what you did in lab 2 for the Muffin Sim. But the difference in lab 2 is that the arrivals there always happened every minute, whereas in the homework, it was more like this. So that's where we are. That's where we left off. Before we move forward to see how to do this in a spreadsheet where you automate some of this a little bit, are there any general questions about how to populate this table now that hopefully, a lot of you have done the homework or, did last week's lab? Any burning questions or issues? Okay. All right, so let's then think about, if we, so the review so far is that these are the terms that I want you to make sure that you know by now. So, or have a general idea of, you could give kind of rough idea of a definition of. So a system or a dynamic system is a collection of entities and resources that interact over time. A model is an abstract representation of that system. So models answer what if questions. So, if I have my system that's sort of in my mind of the thing that I'm interested in doing work with, then my model is a version of the system that allows me to say, what if I made this change to my system? How would the output change? So that's what we mean by model here. In a dynamic system, it has a notion of state. That's the thing that is changing over time. Every dynamic system has some state. Usually the state is stored in a state variable, and if you know the state of the system at any instant of time, if you know the whole state of the system, theoretically, you can restart the system from that state, and then it will move forward again. So the state is usually everything you need to regenerate the trajectory later. Now, you might say, Ted, there's random processes involved in here, and we'll talk about one of the cool things about doing computer simulations with randomness, and this will come up later, I think post midterm, is that we can actually engineer the randomness so that we can actually regenerate the same random numbers over and over again. So there will be a special, I don't want to call it a state variable, but a special number that if we keep track of and we keep track of the system state, then it is possible for us to rewind time and then replay time again, but maybe monitoring more things this time. So that's actually possible to do, of course, only in a computer sim. In a real world experiment, it's not possible to rewind time and replay. But the system state theoretically are the collection of variables that if you knew all the physics of the universe and you knew all the state variables, then you could combine those physics with those state variables to rewind, to restart the universe at that time and then replay it forward, and everything would be exactly the same. The state in our discrete event system simulations changes at these countable time units that we call events. So it doesn't change continuously like the temperature in this room. It changes only at these discrete events. And we keep track of the system time using the clock. It's sort of a state variable that's always behind the scenes. Entities are the focal objects of interest. Those are usually the things we're generating most of the stats on. They can differentiate themselves by their attributes. We have lists in our simulations, which may be special kind of time or kind of state variables that allow us to store collections of objects that we might need to use later. For example, when delays have gone away, like so if a delay has finally been removed from the system, we might need to grab things from those lists. And then event notices. So there's a very special type of list in our system, the future event list, which is also known as the event calendar, or sometimes just the schedule. And in it has a list of these records we call event notices, which tell us what is about to happen in the future, what type of event it is, and any supporting information about that particular event. And it's possible to go into programs like Arena, and it's not by default there because you usually don't have to look at this because it's kind of behind the scenes. But if there's something weird going on in your simulation, then you can actually ask Arena to show you its schedule, its event calendar, its future event list. And you can then see its event notices, and it will say, this create block has an arrival scheduled for this particular time. This process block has a service completion scheduled for this particular time, and so on and so forth. Exactly what you did in your homework, but you get to see that that's what the computer is doing behind the scenes, and it's doing it at huge scale. And then activity versus delay, which we talked about earlier here. Activity is the thing you know before the sim. Delay is the thing you get out of the sim. So activities are inputs, delays are outputs. So that's kind of the major terminology from this section. So any questions about those terms? I might add that, for event, we talked about primary event. Those are, the things you schedule. Those events we sometimes refer to as primary events. They're the things that you put on the calendar because you needed an activity to end. Okay. All right. So I'm going to skip that one today too. So the spreadsheet examples here. So the bonus in the homework says all that hand simulation, try to implement that as a spreadsheet. I don't mean just write out your table in the spreadsheet. Try to actually make it so that you can dump that table of inter-arrival times and service times at the top of a spreadsheet, and then suddenly it will fill out the rest of the sim for you in at least some format. And then if I were to change the inter-arrival times, it would change the output automatically. That's the idea here. So it's the idea of using the computer to make it much easier to deal with these discrete event system simulations. Now, if we think about how to build a computer program that solves these things, then there might be certain programming languages or programming frameworks that are going to be better adapted for these discrete event system simulations than others. And so if we sort of bin programming languages up, there's kind of these major categories. So there's procedural programming languages. So these are like C, Fortran, Pascal, BASIC, sort of more older school programming languages. And so this isn't that important for you to know. I'm just sort of motivating, where spreadsheets come into play and what we need to know when we're trying to implement a DES in a spreadsheet. Now you might say, we're engineers, we certainly should be more sophisticated than being able to use spreadsheets. And that's generally true, that you will be the one in the room who should hopefully know a lot more sophisticated tools than Microsoft Excel. But many of those stakeholders that you work with, they will want something that is more tangible in the deliverables. And so, for example, and there are government entities that actually don't allow you to work with software programs other than certain ones that have been approved. So I have colleagues that work with the NIH, and they have to implement all of their operations research in a Microsoft Excel, not Google Sheet, spreadsheet, because for those projects, that's the only thing that's approved for those types of data. And so things that they would normally have to code up in R or Python or whatever, well, these open source packages aren't available for these particular government projects for security, privacy, and other sorts of reasons. Probably lobbyists, probably corruption, to be honest. But regardless of it, engineering is all about constraints, and you're constrained in some of the tools you can use. So even though it's kind of boring to think, why would I bother coding all this stuff up in a spreadsheet? It still ends up, you find it being very practical, and you find weird things too. Like I was talking to somebody at the DHS, Department of Homeland Security, and they were talking about the things that they look for in engineers, and things that I would have expected them to, 20 years ago are still very hot. Like if you know Visual Basic for applications, the programming language that's sort of built into Microsoft to allow for scripting and macros and things like that, that's actually a hot commodity for people trying to get certain types of high security government jobs, because again, they're very limited in what they can do, and yet they still need automation and sophistication. So those who have those skill sets actually have a competitive advantage. So there's weird things about the tools you can use. And so that's why I'd recommend just learn as many tools as you can and be very flexible. So getting back to it then, procedural programming languages like these are so-called imperative programming languages. And so what we mean by that is that you write code where statements of code, lines of code, change the state of a program. So the state of a program is like, you got a variable, x equals 5. Well, then later you say x equals x plus 1. Well, now x is equal to 6. So every line of code is changing the state of the program. That's why you make imperative statements, which refer to the current state and then move it to the next state. Then there are object-oriented programming languages like C++, Objective-C, Java. These are ones where sort of built on top of procedural frameworks, where now instead of keeping the state variables separate as separate variables which are being operated on, you bundle them into data structures where the variables are hidden inside a structure, and the operations that happen on those happen sort of on the objects. And so rather than saying, I'm modeling a house whose lights are on or off, and you have a line that says lights equal on, lights equal off, instead of that, you just say, I'm instantiating a house, and then I'm going to say house.turn lights on, and then inside that object, it's going to change its internal state. It's almost like an attribute of that object, but it's still basically the same idea, that there are steps that you have to go through to change the state of the program. And then there's functional, which is qualitatively different. So examples of this: Lisp, Common Lisp, Scheme, Haskell, ML. So there's Camel. There's a bunch of different examples of these functional languages, and there are hints and whiffs of functional languages in things like NetLogo, Python. Even there's a little bit of functional in there. Although the guy who made Python is not a huge fan of functional, so stripped out a lot of the functional and replaced it with some other things. But functional languages here are what we refer to as declarative. And so the program output is a mathematical function of its input. You don't actually say how the program does its work. You just sort of say what mathematical relationships should be true at the output of the program. And then somehow behind the scenes, the program makes those things happen. And so they don't have these side effects that change the program state. There is no state. There's just functions. I have these inputs. I have these constraints on the outputs. Given that my inputs are this, and these are my constraints on the outputs, I can be guaranteed my outputs will have this guaranteed relationship to the inputs and meet all these constraints. And we have no idea how that happened, but that's how the declarative programming languages works. And spreadsheets are an example of these. They're one of the first popular functional languages. And so if you think about a spreadsheet, it uses, this is also known as cell-oriented data flow programming. So the idea here is, hopefully you've all used a spreadsheet at one time or two, and you know that you don't specify how the whole spreadsheet works. You just specify how cells are related to each other. So you say that, this cell is always twice this cell, or this cell is always the sum of these cells, and so on and so forth. And so if you think about it, like if you've got all of these relationships in here, it's not clear that like once you edit a few numbers, what happens first? What cells get updated first or second, whatever. You don't know any of that. All that has been abstracted away from you. All you know is that after a short amount of time, the spreadsheet will show you outputs that will meet those constraints that you put into the cells. That's what we know as a declarative programming. You didn't actually tell the spreadsheet how to populate each cell. You just told it that once you're done doing whatever you're doing, this is how the cells should relate to each other. So there is no notion of state in a spreadsheet. There's nothing that's marching forward through a recipe in a spreadsheet. So then it suggests a challenge of like, well, how am I going to simulate a discrete event system simulation that has state? That is fundamental to a discrete event system simulation in a framework that has no state. And that is what makes it a little bit interesting. And so that's what we have you do in the bonus of homework B1. So here's an example of how to do that. So this is an example of what you'll do in the bonus as well. So this comes from chapter 2 in the Banks book, table 211, page 47. If you want to look into more details of this, this is how you can imagine starting such a spreadsheet up. So here, this is captured. So for every customer, there's their service times, and here's their inter-arrival times, where the first inter-arrival time is 0, and here's the initial conditions. So they arrive at customer 1 arrives at time 0, their service immediately begins, and then this is sort of this is kind of getting ahead of ourselves, but we know that their service ends because their service time is 2, and it immediately begins at 0. So the idea here is that now we've spread out the execution of the program, not across time, but across customers. So now we're going to rethink the discrete event system simulation model, not in terms of what's happening from time to time to time, but how customer to customer relates to each other. And if we can think about those relationships, then we probably can come up with constraints that allow the spreadsheet to give us the outputs in a slightly different form than our hand simulation, but with all of the same information. So let's see how we can do that. So one of the relationships we know that must always be true is that the arrival time for any customer is the previous arrival time plus the inter-arrival time associated with that customer. So if I look at these 3 blue marks here, then I can see that for customer 4, they have an inter-arrival time of 4. The previous customer arrived at time 10, so 10 plus 4 gives me 14. So if I were to implement that in these cells and fill them down, then I could get all of the arrival times are basically the cumulative sum of all of the inter-arrival times, just like I was saying at the beginning of this lecture. So that's easy. I can just fill that thing down and I've got all of my arrival times. Now I have to think about more complex relationships. And so the next one, slightly more complex, is at what time does the service begin? What is the relationship on every single customer that represents how the current service time beginning relates to some properties of the previous customer? It's always like looking at the things we know about the current customer and things that we calculated from the previous customer. And so here we see that the time the service begins for any customer is the maximum of 2 numbers, and that is that customer's arrival time or the previous row's service ending time. And I say the maximum of those two because what we're sort of saying here is if you arrive before this previous customer's service ended, then you have to wait. So your service time will be when the previous customer's service ended. But if you arrived after, so your number is greater than that, when the previous time ended, then your service will begin exactly at your arrival time. So we can put that relationship down. We can code that up in, Excel has a maximum function, which does some, looks very similar to this. And we can code that up right here. So we can say the service begins as a maximum of this cell and this cell. And so I see that the previous customer ended at 2, I arrived at 5. So in this case, my service will begin at 5. And so then I theoretically can fill this down. Now the trick here, and this is a declarative programming trick, is if I fill this thing down, immediately it's not going to be meaningful because this time service begins here depends on the time service ends. And I haven't put in a formula for time service ends. So that's a question I'll often get in office hours and things, is when students start writing this out, they say, Ted, when I filled this down, it was said like 5, and then it gave like a bunch of zeros or something. And I know that's not right. I must have done something wrong. And I said, no, you have to have patience because the declarative programming language requires you to lock in all relationships before you can trust the outputs. And you haven't put a relationship in this column yet. So it has to use the dummy info in this column. And once we populate this with the right relationships, then these will lock into place. All right, any questions so far about where I'm getting these relationships? Again, I'm not doing time by time by time, I'm doing customer by customer. Okay. All right, so next thing here, the waiting time in the queue. So I'm just going from left to right. I could have gone to time service ends next, but it doesn't really matter. I need to populate everything for anything to start making sense. And so the waiting time in the queue, that relationship would say, well, for every customer, how do we get the waiting time in the queue? Well, that doesn't depend on the previous row. That's just stuff that I know in this current row. And any customer's waiting time in queue is just going to be the difference between when their service began and when they arrived. So for this particular customer, their waiting time is just their service began at 18, but they arrived at 16. So the difference between those two is 2. Most of these customers didn't have to wait, so their service beginning time matches their arrival time, and that's why it's 0. So then I have to think, moving left to right, what's the relationship that holds for the ending time? Well, for the ending time, that's easy. That's just going to be, if I know the beginning time and I know the service time, the ending time is just the sum of those two. And so I have another column here, service begins, and I have service time. So in order to get this 21, I just took, well, their service began at 18 and it was 3 long. So that's what gave me the 21. So now I know when their service ended. So I know when they depart the system. So how long do they spend in the system? Well, that relationship will always be for every customer, the time that their service ended minus their arrival time. So up here, this customer 5, I got that because their service ended at 21, but they arrived at 16. 21 minus 16 gives me that 5. That's how long they spent in the system. And then the last thing that I'm interested in is how long was the server idle? And so the idle time, this is another one of those slightly more complex ones here. But I could say, well, what's the relationship that always holds in the idle time? So in the number of minutes that server sat without a customer. And so we know that the idle time of server is going to be either 0 if there's no idle time, or if there is idle time, it's going to be whenever the service began minus the previous row's service ending time. So if I look at this highlighted example here, this 5, then what we're saying here is that the service of the previous customer ended at 34, but the next customer didn't start in the server until 39. So the gap between this here was the idle time in the server. So this server, before servicing this customer 8, the server sat idle for 5 minutes between customer 7 and 8. That's what this is saying right here. And if these two happen to be negative or 0, then we take the 0. And so in these cases here, like this one here, the service ended at 18, but then it began at 18. So 18 minus 18 gave me the 0 here. So this case, the server is continuously working. Here, the server gets a little break. And that's the last relationship I have to populate to get all of the info out. So before we highlight a few things here, are there any questions about any of those relationships there? Yes, I'm sorry. The bold columns, so these 3 columns, service time, interarrival time, and customer. You change those, and the rest of the table will change. That's right. And these, in the case of the homework, I give you all of these service times, all of these interarrival times, and all of the customer IDs. But then if you were to get, like, if you were to help, another student out with another example, and you just came up with other, like if you were to go back and to look at some of the previous years to see how those work, you could then dump the service times from those previous years' assignments and the interarrival times from those previous years' assignments in, and then it would automatically populate that, and you could then confirm that it matches the hand simulation in those old solution sets. Was there another question in the back? I thought I saw. No, okay. Any other questions about this? Yep. No, right, yes. Yeah, the VBA comment was just an anecdote that heard directly from a colleague at DHS, but in this case, no. Yeah, the VBA would be if you actually did want to implement state, then you could use VBA as an imperative language to then you could say, you could put, like you could imagine putting the first row of your hand simulation in and then using VBA to iterate, where it would automatically say, all right, based on your first row, I'm going to generate the second row, generate the third row, and so on. But it wouldn't be this sort of instantaneous thing that snaps into place. So yeah, the VBA solution would be uglier for me to present here, but it would look much more like the kind of arena-based hand simulation. Okay. So the key thing here is that in our hand simulation, we spread out the solution across time, but in our spreadsheet simulation, we spread out the rows by space. So the relationships are between customer and customer, and also time is involved here too. But if you want to get time information out, time is sort of like, notice that all of these columns. This is this is a time column. This is a time column. This is a time column. So if I want to ask questions about this, like these cumulative statistics, if I want to generate these cumulative statistics, I have to sort of be clever about where I look for those. So for example, like let's say here, I want to know at what time did customer 13 depart? Well, here I see there's a departure event was generated, time 13. So customer 3 departed at 13. That's actually kind of easier to do in the spreadsheet. I go to customer 3, I go over, that's when they departed, 13. That matches. But if I want to look at these like cumulative statistics and things, I'm like, so this here, we're saying that when customer 12 departed, then customer 12 added 8 to this S column here, which is the sum of the response times. And then when customer 13 departed, they added an additional 7. So if I look down here, I see, well, customer 3, they departed at 13. They arrived at 6, so that they spent 7 in the system. So if I want to figure out where do I get these, like 9 and 16, it doesn't show up immediately in this column. I end up having to sum these things up. So if I want to know the cumulative statistic up to customer 3, well, I have to add 1 and 8, and that gives me my 9. And then I have to add that 9 and 7, and that gives me my 16. So this column here requires some kind of post-processing of this table. Of course, I could have created a cumulative statistics column that just adds these things up as I go, for sure. And kind of what I'm showing here. So it's hard to see in green, but 1 + 8 + 7, that gives me my 16 right there. So you can get all of the data from this table up here, from this table down here. It just might require you to look in a slightly different place. All right, so any questions about that? So when you do your homework, that's another sanity check, is that if you implement the spreadsheet and you feel pretty good about the spreadsheet, but if you're getting different departure times than your hand simulation, then maybe check into your hand simulation logic or vice versa. So those two should agree. Like when I look at all of these departure events, so customer 2 departed at 12. Customer 5 arrived at 16. Well, down here, customer 5 arrived at 16. Customer 2 departed at 12. So those match. All right, any other questions about that? Okay, great. So now, regardless of how you do it, there is significant variability within and between replications. So we have to generate new experiments, but if you rerun this same simulation with the same arrival times, or sorry, the same inter-arrival times and the same service times, you'll get exactly the same output. So the way that we're going to generate variability is by generating new random numbers for inter-arrival time and service time. So that's why it will be important for us to not just have a list of service times and a list of inter-arrival times, but post-midterm, when you do this sort of stuff, then you'll have a distribution of service times and a distribution of inter-arrival times. And so you'll be able to draw random numbers, and that from a distribution that matches so across replications, it'll have the same mean and the same variance, for example, but for every replication, you'll get different numbers. And by generating different numbers for inter-arrival times and different numbers for service times, you'll get different numbers of all of these statistics. And that'll allow us to run like multiple replications of the same system. But you could imagine like one's Monday, the other one's Tuesday, the other one's Wednesday. And then we can then do statistical analyses. And that's all I'm trying to get at down here, is that we're going to have to run stats on our simulated experimental systems. And we're going to have to struggle with things like, how many replications do I run? And how do I reduce the number of replications? And that is going to directly relate to the lab 2 stuff here in a second. So, and we have to again use stats. And so this empirical system is just as variable as this empirical system. And just like you definitely have to use stats when you do this lab work, you'll definitely have to use stats when you do this simulation work. And yeah, so that's all I've got before we do the post lab 2. So any questions about this? This is the homework stuff. Feel confident that if you want to give it attack the bonus, you've still got time to do that. All right. All right, well, let me flip to post lab 2 here. All right, so lab 2, about this muffin baking operation, right? So this is the question here is like, well, what are the entities here? Individual muffins or batches? So there's different ways that you can address the questions that were brought up in this lab. So you can model the muffins as individual items. And this is easy to handle, limited oven capacity, but you have lots of simultaneous arrival events. And so there's a huge number of muffins that arrive at once, and so they all have an inter-arrival time of 0. And that is sort of can be difficult to deal with when you're talking about these distributions and so on. So the simultaneous arrival and departure events might be something that we want to avoid. And so in that case, rather than modeling each muffin as an entity, we might make the choice to modeling the batches of muffins as entities. And that way you only get one batch arriving at a time. The downside, as I hope you saw in the lab, is that if you model the batches as the things that arrive, then if you want to put a batch of muffins into the oven and there's not enough space because the oven is got capacity in terms of muffins and not muffin batches, then you have to create partial batches. And so that's one of the things that we're also trying to get out of this lab, is to sort of expose you to the idea of that you can have batches that arrive and then get broken apart during the sim, possibly put back together, possibly not. So that's another concept that we're trying to cover here. And it's possible to use both types of entities in one simulation. So you can temporarily unpack a batch, handle each muffin separately, put them all back together in a batch, and let the batch keep going. So that is another sort of thing that it's a more advanced topic that you'll see towards the, I think lab 10 actually is when we start playing with batches more explicitly in Arena, but it's something I want you to at least have on your radar. Now, this idea of this muffins versus batches and just generally deterministic arrivals, the stochastic quantities, that's the key difference here between the muffin sim and the customer simulation that we've been doing on the other side of things in lecture, is that we've been spacing customers randomly from each other. In the muffin sim, I hope you caught that the muffins always arrive every minute, but there's a different number of muffins every minute. And that is very common for example, stochastic models of stock price data. So this is like, every day the price goes up or down. So it's not a question of whether the price will change tomorrow. It always will change every 24 hours, the average for that day. But then you might want to model whether it's going up or down, and you might want to then, be able to sort of play with that to sort of say, if we've got prices that have certain upward trending trajectories or downward trending trajectories, how do we build portfolios that maximize our profit? And so there are a set of financial researchers that use the tools that we talk about in this class to build these muffin sim-like models where instead of imagining muffins arriving every day, they're imagining prices going up and down every day. And instead of modeling what operational policy you use for your oven, they model whether you buy or sell stocks. But otherwise, the math behind it all is basically the same. And so you're studying, how much delay does a muffin have in, whether it goes through this oven or not as it's waiting to get access to the oven. They're studying whether I've sold a stock that price ended up going down, and does that, end up hurting my profits or helping my profits. And so there's all of this sort of fancy modeling that's outside the scope of this class. Called martingales, which are these processes where the expected value of tomorrow's price equals today's price, and that's how we model this sort of variability. But that's another thing that I want you to at least get a whiff of with this muffin simulation, is that this idea of a random thing happening on a deterministic clock, there are a lot of other systems that have that structure. And but let's just focus on the muffin sim here. And so what we did in the muffin sim is we said there were, let's say, two strategies that we're interested in: greedy and nearly full. And so the idea here was that a greedy strategy, immediately when muffins arrive to the oven, regardless of how empty the oven is, you just put the muffins in the oven and let the oven go, with the complication that oven will not be able to be accessed again until those muffins are done baking. So that might mean that muffins stay queuing up, waiting for the oven to finish. The alternative is nearly full, where you pile the muffins in, and once they go over a certain threshold, then you let them bake. But that means muffins are going to have to sit and wait for more muffins to arrive. So it's not completely clear where you're going to get more wait time. It kind of depends on how quickly muffins arrive. So, you might imagine in some scenarios, it will be worse to do the greedy cycle because you're going to get a bunch of muffins that arrive that you could have loaded up into the oven, and now you've got an underutilized oven. But in the other case, if you're waiting for full utilization of the oven, then and it takes a really long time to get enough muffins, you may have well just baked the muffins that you had. And so that's what we're kind of comparing, is that for different arrival schedules, what's better? And so what, if we give you the same arrival schedule, we can run it through the muffin sim and calculate the average time total in the system per muffin. And let's say down here, it's 3.9 minutes versus up here, it's 4.2 minutes. And so this is, and I want to emphasize, the same batch schedule. Now, the two problems here is that, one, do we have statistical significance? Well, we don't know because there's only one data point. But even if we could call this statistically significantly different, then is it practical that 3.9 minutes versus 4.2 minutes? It doesn't seem like a big difference. And so estimating whether there is an effect, that's the statistical problem. And then estimating the size of the effect and whether that effect size is big enough, that is a practical problem that is subjective. So those are things that I'm hoping to highlight here. Now, in your sim, we used your ASU ID, that last number, to sort of basically give you all a different random schedule. So this is like I was saying earlier, where in order for us to generate variation in the outputs, we need variation in the inputs. Well, we gave you 10 different muffin schedules, but then over the classroom here, then each one of you were running a different type of replication. So if your ASU ID ended in 0, you were running replication 0. If your ASU ID ended in 1, you're running replication 1. So you were all running the same logic, but you had different arrival schedules. So some of you had 5 muffins arriving on day 1, others of you had 10 muffins arriving on day 1, and so on. And so if we take all of your data from lab 2 and put it on one graph, this is what you get. This is what you get when I run all 10 of those schedules and aggregate them together. It looks like this. So this circle here, this was the, I think, original one, and then I've just added the other 9 to it. And so when I look at this, I've replicated the experiment so that I can try to detect a statistical difference. Now, when you look at this, I hope you see that it looks like the average time for the greedy is lower than the average time for the nearly full. And you might do, well, does anybody know, what is the statistical test that we use if we're trying to compare averages? We have data like this, and I want to say, does this population have a lower or greater or different average than this population? What's the statistical test we would use for that? A 2-sample t-test, right? The hint right here, 2-sample t-test. But you can't do that with these, because a 2-sample t-test, and this is the hidden little thing that often is in the subtext of whatever 380 or 385 when you get exposed to a 2-sample t-test, is that you can only use a 2-sample t-test if all of your experimental replications are independent from each other. And they weren't, because one muffin schedule, every point here has a point over here that use the same muffin schedule. Now, if I used 10 muffin schedules for greedy and another 10 for full, then I would use a 2-sample t-test. But because I used 10 muffin schedules that generated both a greedy number and a nearly full number, I'm not allowed to use a 2-sample t-test. It violates the assumption of the test. So, so this is what statistical test that I just asked there. But, I can't, because they weren't drawn independently. So the idea here is that why did we not draw them independently? Well, this is something that after the midterm, we're going to talk about common random numbers. And that's what we were simulating in lab 2, is common random numbers. This idea that I'm going to take 2 different sims, 2 different models, and I'm going to run them with the same random numbers into both. That method, common random numbers, creates pairs of treatments And this is an example of what we refer to as statistical blocking. It creates blocks where you say that, you know, there is a greedy and a nearly full that are paired together. There is a block there. And why would we do this statistical blocking? It turns out that it will reduce the amount of variance that we have and increase something called statistical power. So what I'll show you in a second how this works, but the kind of anecdotal example, whatever, the common example is with shoes. If I have an orthopedic shoe and a running shoe, and I want to see, you know, the benefit on, I don't know, foot pain or something like that. And I could get 100 pairs of orthopedic shoes and have 100 people put them on and have them wear them for a month. And then I could get 100 pairs of running shoes and have 100 other people put them on and have them you know, wear them for a month. And then after a month, I could ask them, both groups, what's your foot pain like? And I could compare those two. But what might happen in that case? Like, let's say I find out that the running shoes people say that they have a lot less foot pain than the orthopedic shoes. What is a potential confounding effect that might have happened just by bad luck? Anybody have any thoughts about that? Like, I ask 100 random people to wear one type of shoe, another 100 random people to wear another type of shoe, and then I make an inference that any difference that I detect in those two populations is due to the shoe. What's a logical flaw in that argument? Yeah, the people. Say it again. That's right. If I did a bad job at picking my 100 people, it might be that the people with the foot pain naturally had more foot pain than the other people. So I need to somehow be very careful about how I randomly draw these things. Or because there's 2 shoes and 2 feet, I could do something crazy. I could say, I'm only going to grab 100 people, not 200 people. I'm going to put a running shoe on one and an orthopedic shoe on the other. And I'll have every person wear 2 different shoes, and I'll randomize which foot gets which shoe. So for you, your left foot's orthopedic. For you, your left foot's running, but your other one is whatever the other shoe is. If I do that, then even if I have some people that naturally have less foot pain than some others, I can now ask about the difference. For you, how does your left foot feel versus your right? For you, how does your left foot feel as your right? And now every person becomes a difference. And now I don't have to worry about the differences in populations because the blocking has allowed me to zoom in on an effect that is entirely due to the shoe. So even though the big effect in pain might be due to population, by making everyone wear both, then I factor out that source of variance. So the only thing left over is the difference between the shoes. That's what we do here with our muffin schedules here. There are some muffin schedules that just might be naturally better for greedy or naturally better for nearly full by giving each muffin schedule, allowing them to sort of have both, then it's kind of like having each person wear both shoes. And so that's what we should do when analyzing the muffin results, is that this is a common way we output these type of data. And this is the statistical test I'll use is what's called a paired difference t-test or a paired t-test. And the idea behind a paired t-test is that these data are related to these data in some way. So I'm not going to do a 2-sample t-test where I'm looking at this mean versus this mean. Instead, I'm going to do a little pre-processing where I'm going to connect every point that had the same schedule. So this is ASU ID ending in 0, this is ASU ID ending in 1, and so on and so forth. And I'm going to connect them to look at the differences. And I'm going to say for every muffin schedule, notice that the slopes of these lines vary a lot. So there are some muffin schedules that really give nearly full a disadvantage because it's better to be lower. But there are other muffin schedules like this one where there's hardly any difference between these. But what do you notice, regardless of the size of the effect, about these lines? What was that? They're all moving in the same direction. So yeah, if you're looking from this way, they're all moving this way, or they're all moving this way. regardless of the slope, all the slopes seem to have the same sign. So that gives me the idea that that if what I might be able to do, and this is what we do with, this is exactly what goes on in a paired difference t-test, is if I take the differences. So now I'm going to subtract, like every one of these red lines, I'm going to take this blue dot minus this red dot, or this blue dot minus its red dot. And I'm going to take each one of those, and here, this is the end of your ASU ID, and this, there's the nearly full strategy, here is the greedy strategy, and here's the difference between them. So this is another way, a common way to plot paired difference t-tests in this direction. And what we notice when we plot it this way is that the red dots are almost always, in fact, in this case, always above the blue dots. So we can now see an effect that if I did not connect these with these dashed lines, like if I were just to go back and to look at these data, then there's a lot of overlap here. So it doesn't look like, it looks like there is an effect of greedy versus nearly full, but it does not look as strong because there's significant overlap here. For all I know that, for all I know, these two were paired together. But when I actually highlight who was paired together, then suddenly it allows me to zoom in on an effect and magnify it, where now it's true, sometimes I have small effects, and sometimes I have large effects, but the sign of the effect is always the same. So now I can look at this and turn this into just a set of differences. So these are now all of those differences. And now I can do a one sample t-test and see, do these differences differ from zero? And that is all a paired difference t-test is it takes your statistical blocks, subtracts the differences, and then compares the differences to zero. And here, it's clear that this whole population has a mean which, with 95% certainty, does not include zero. It is not zero. So the confidence interval of this mean does not include zero. So, and it's negative. So this tells us that there likely is a strong effect of this greedy versus nearly full. So in this case, greedy minus nearly full, that is negative. So that would tell me that greedy is generally smaller than nearly full. So that is why we block, is because it allows us to zoom in on these effects. So things that had a little bit of overlap and uncertainty initially, because we had a blocked design, there is really no uncertainty here. It's pretty darn clear that across a wide range of muffin schedules, greedy is better. So that's something, again, we're going to talk a lot more about that post-midterm in variance reduction techniques, but I want you to have exposure to that now, because that's exactly what you did during the muffin sim, is common random numbers to reduce variance so you can amplify your statistical power. So you've done it already, and we're going to talk about exactly why it works after the midterm, but you've already seen it. So questions about that general idea? See what we did there. Now, there's a lot more that we can say about that hints at other things that we need to worry about throughout the semester. So for one, we had you calculate not only the average time in system, TIS there, we also had to calculate average oven utilization and maximum queue length. And so if I look at this, average time in system, there is clearly an effect of greedy versus nearly full. But if I look at average oven utilization, it doesn't look like there's an effect. And if I look at maximum queue length, it doesn't look like there's an effect. And I had to use something called a signed ranks test instead of a paired difference t-test. And we'll talk about why I had to use that for that type of data later. But the point is here, 3 different outputs. One of them says there's a difference, the other 2 don't. So is there a difference? You might say, well, there's one that's a difference. That should be good enough. But remember, each one of these there's a 5% error rate on each one of these p-values. So, or I want to say on each of the p-values, each one of these tests. So just because this p-value is less than 0.05, if that was my only output, I'd say, okay, that's good enough for me. But I'm going to get that wrong 5% of the time. So if I accumulate a bunch of these things, then I will eventually, by accident, find a metric, a key performance indicator that's different between the two groups. And if I use a 5% criteria on that, then I'm going to inevitably make an incorrect conclusion if I say there's a difference between these two strategies just because one of these KPIs shows a statistical difference. So that's going to be an issue that we have to deal with as well. How do we deal with this when we have multiple outputs? One of the ways we'll deal with it is we'll say that every comparison you make, every output you make, you have to change your alpha value. So it's 0.05 if there's only one output, but if there's two outputs, it's 0.025. If it's three outputs, it's 0.05 divided by 3. And if you keep doing that, then that's something we call Bonferroni correction, and that will help guarantee that the family error rate is 0.05, even though but that sort of forces us to make the individual error rates much less. That's something that we'll have to deal with, and we'll talk about a lot more in the rest of the semester. And so there are other ways we can do this. There are other tools other than t-tests. There's a multivariate ANOVA. There are tools that are meant to work directly with multiple outputs. And so multivariate tools, and then again, the Bonferroni correction that I just chatted about there. These are not things I'm expecting you to know now, but these are a hint of the things that will come in the rest of this class here. And then of course is the difference practically significant. That's where regression tools will be useful. So we're not going to talk that much about regression in this class, but you have talked about regression. And I hope you can see that in the Muffin Sim, it's silly to talk about greedy versus nearly full, because really it's a ordered threshold. So it's whether your oven threshold is 1 versus 30, or 1 versus 25, whatever our nearly full is. We could just throw all the other thresholds on there and then study the pattern as you increase the threshold. And that will give us a better idea of the effect size of increasing the threshold by 1 muffin, and so on. And so we can plot all those output metrics for every threshold, which is what I did here. And we can then fit regression lines. And so we can sort of get an idea about, through linear models, what the rough idea for every muffin, how much do you increase the time in the system? So we can study interaction effects with linear models. So these are all the things that by interaction effects, it's using this idea that you can have that sometimes, so notice here, the result is going up. But if I go over here, where my service time is now 7, so here the service time is whatever it was. I forget what the default service time we gave you was. But when I change it to 7, this slope goes the other direction. And then this slope starts increasing, even though it was flat there. So that's the other cool thing about using regression models, linear models, is we can start studying not just the main effects, but the interaction effects of not just how does service time affect my performance, and how does oven threshold affect my performance, but how does the interaction of the two of them affect my performance? And that would suggest that in certain regimes of service time, I have one recommendation on oven threshold, but in other regimes of service time, I have another recommendation. So that's why when you start doing this in the real world, you'll be using much more sophisticated statistical tools than we'll start out with here. But we have to start somewhere. And that's all I was kind of saying there. So any questions about that before I give you the one clicker question for today? All right, so in that case, let me pull up iClicker. All right, so so should be running. Question is, if I do not have a independence of my two groups in a t-test. So I want to use a t-test, but I don't have independence. What is an alternative test that I can use that hopefully you also heard about in 380 and I mentioned here? So a two-sample t-test, I need independence between my two groups that I'm comparing. If I don't have independence, what is the alternative, I'll say it, the alternative t-test that I should use to deal with losing independence between my two groups? So there's multiple types of t-tests. It's not the two-sample t-test. So what is it when I have lack of independence between my two groups? And that's all I've got for you. So we'll see you Thursday. Don't forget homework B1 due tonight. Uh-huh. Like the way I went about this first one. We're gonna review it. Oh, probably. I'm just gonna stop the recorders. Let me sorry, I just want to make sure